A very happy new year to all my viewers. May 2021 bring lots of hope, happiness, and prosperity to all of you and your family. My name is Shalini Singh, and this is the third part of the Open Channel Flow series. The link to the first and second part is given in the description box. The contents of this video are energy principle, momentum principle in open channel flow, and concepts of specific energy. In the one-dimensional analysis of steady open channel flow, the energy equation is used in the form of Bernoulli equation. And according to this equation, the total energy at a downstream section here will differ from the total energy at the upstream section here by an amount equal to the loss of energy between the section, that is HL. For steady flow of an ideal fluid, the summation of the datum head Z, the pressure head Y, and the velocity head V square by 2g must have the same value at all sections. If the streamlines are fairly straight and parallel, and the slope of the channel is small, the pressure distribution over flow section is hydrostatic, as we can see here. P will be equal to gamma into H. And in case of gradually varied flow, the curvature of streamlines is very slight, and so there is hardly any departure from the hydrostatic distribution of pressure. And so here also P will be equal to gamma into H. In open channel flow problems in which the channel slope is not very large and the flow is other than rapidly varied flow, the pressure distribution over a flow section can safely be assumed hydrostatic. So if you see in the figure, H is equal to T into cos theta, where theta is the angle made by the slope and the horizontal datum. So cos theta, when theta will be very small, will be equal to 1. So H will be equal to D. So P can be given as P equals to gamma into H. Now, here the given figure shows a channel of small slope. So at point A, if we see here, which is at a depth of H below the free surface, the pressure according to hydrostatic law will be equal to gamma into H, and the piezometric head will be H plus ZA. Now H plus ZA will represent the height of the free surface above the datum level. So the free surface will be the hydraulic grade line. So this will be the hydraulic grade line. In ideal fluid, the velocity does not vary across a section, and hence the Bernoulli equation at a flow section may be written as ZA plus H plus V square by 2g. And if the fluid depth at the section under consideration is Y, and the elevation head or datum head of channel bottom above the arbitrary horizontal datum is Z, then ZA plus H can be written as Z plus Y, and the Bernoulli equation can be written as H equals to Z plus Y plus V square by 2g. Here H is the total head, and which is the total energy at any section. The assumption of ideal fluid results in a uniform distribution of velocity over a flow section, which is never achieved in practice. So the Bernoulli's equation, after having corrected for the non-uniform velocity distribution, may be written as Z plus Y plus alpha into V square by 2g, where alpha is the kinetic energy correction factor. Momentum principle. The Newton's second law of motion states that the change in momentum per unit time in a given direction is equal to the resultant of all the external forces acting on the body in the same direction. So considering a channel of large slope as shown in the figure and applying the momentum principle to the water contained between section 1 and 2, here the controlled volume would be the body of water bounded by sections 1 and 2 and the wetted perimeter P and the free surface. The momentum of flow entering section 1 per second is gamma into Q by GV1, where gamma is the specific weight of the flowing liquid, and the momentum leaving section 2 will be gamma into Q by G into V2. So the external forces acting on the body of water enclosed between sections 1 and 2 are P1, the hydrostatic pressure force at section 1, P2, the hydrostatic pressure at section 2, and W sine theta, which is the component of water here, enclosed between the sections in the direction of flow, and RF, the resistance force due to friction between channel surface and the liquid, which acts along the contact surface. Now, applying the momentum principle, we'll get gamma Q by G into V2 minus V1 be equal to P1 minus P2 plus W sine theta minus RF. So this equation is known as the general momentum equation applicable to open channel flow. Specific energy. Now the total energy of flow per unit weight of liquid is given by Z plus Y plus V square by 2G, where Z is the elevation of the channel bottom, Y is the depth of the flow, and V is the average velocity of flow. So if the channel bottom is taken as datum, then the total energy per unit weight of liquid E will be equal to Y plus V square by 2G. This energy E is known as the specific energy, which can be defined as the energy per unit weight of flowing liquid measured above the channel bottom and is equal to the depth of flow Y plus the velocity head. So we can see from the specific energy equation that the specific energy comprises of the potential energy flow Y and the kinetic energy of flow V square by 2G. So using the continuity equation Q equals to A into V, E can be given as Y plus Q square by 2G into A square. So E can be set as a function of Y and Q. Now the area of flow A is dependent on the channel geometry and the depth of flow. But for a given channel section, it will be solely dependent on the depth of flow Y and the rate of flow Q. So the variation of the specific energy can be seen in two ways. Firstly, keeping the discharge Q constant, the variation of specific energy E with depth of flow Y can be obtained. And secondly, keeping the specific energy E constant, the variation of discharge Q with depth of flow Y can be studied.
For a rectangular channel, the area of flow will be A will be equal to B into Y, and small q, which is discharge per unit width, will be equal to Q by V. Now E will be equal to Y plus QB whole square by 2G BY whole square. So when we solve, it will get Y plus Q square by 2GY square, which will be a function of Y and small q. This video is the third part of the series on open channel. The remaining parts will be posted in due time. I really hope this video is useful for the students of civil engineering. If you like my video, please press the like button and subscribe my video. Thank you and God bless you all.